Hello, everyone. Good morning, and welcome to day 4 of Climate Week at Penn. My name is Osek Eke. I'm the Director for Local and Global Service Learning Programs at Penn Engineering. Today, we have a fantastic panel that will talk about mass timber as a construction instrument that is used to prevent, or at least to address the issues of climate change, global warming, and of course, sustainability. And today, our moderator will be Stephanie Carlyle. Stephanie is a lecturer at the Weizmann School of Design here at the University of Pennsylvania. She's also a senior researcher at the Carbon Leadership Forum. Stephanie is an architect and ecologist, and she also teaches building technology at the School of Architecture here at Penn. So welcome to our panelists. We have architects, and they'll give us insight into mass timber and how it's used for conservation and also for efficiency of buildings, especially now that Penn Engineering is working on a new building, and mass timber will be part of that building. So we're really excited to have the panel on. Stephanie?
Thank you. And thanks again to Penn Engineering and the School of Design for inviting us all to speak about this important topic. We're really all very happy to be with you here today, participating in Climate Week, and also really sharing how the incredible excitement around discrete actions that architects, engineers, contractors, and the whole building industry can really take to participate in radically decarbonizing the building sector and addressing climate change. So we have a really great panel today and a series of presentations about mass timber, about embodied carbon more broadly, and about a really exciting case study that hopefully is going to tie all of those topics together and make them really tangible and specific. So I'm going to go ahead and introduce all our presenters today, and then we'll jump right into the topic. So we're joined by Terry Pillow. He's the Mid-Atlantic Regional Director for Woodworks, which is the Wood Products Council. Terry has an accomplished background in commercial architecture, project development, construction administration, working throughout the US on a range of projects and occupancy types. Terry strives to bring the strongest solutions to end users based on harmonizing sustainable design within budgetary constraints. And he is an incredible expert on mass timber, both the technology as well as a whole range of interesting ways in which the mass timber industry is growing and supply chains are becoming secured across the US, that he's going to share a lot of that knowledge with us today. In his role, Terry challenges design trends by educating and supporting best practices through smart selection of building materials and methods. We're also joined by Heather Holdridge. She's the Director of Design Performance at Lake Flato Architects. Leveraging a background in mechanical engineering, Heather directs all Lake Flato teams in establishing sustainability goals, and she devises strategies and systems to realize these goals under programs such as LEED, 2030 Challenge, and the Living Building Challenge. Heather works closely with teams to evaluate passive systems and performs energy modeling throughout the design process. And finally, we're also joined by Carrie Phillips, who is an associate at Lake Flato Architects, where she manages some of Lake Flato's largest and most complex projects, with a focus on STEM facilities, as well as the intense renovation needs of our most demanding clients. With more than 10 years of architectural experience in a range of project sizes and types, Terry's talents for creating vibrant, interdisciplinary academic and research environments is paired with a passion to create high-performance buildings. So with that, I am going to jump right into an introduction to the topic of embodied carbon and how it really connects to mass timber as an essential strategy for decarbonizing the building sector. Go ahead and share my screen. All right, is that working for everybody?
It is.
Excellent, thank you guys. And I forgot to mention we have a Q&A feature enabled during this webinar. So if you have questions at any point, please drop them right into the Q&A, and we'll keep track of that during the presentations and hopefully have some time at the end of presentations to answer questions from the audience and have a bit of a conversation between the presenters. So I'm just going to start us off by talking a little bit about embodied carbon in architecture, why this is such an essential topic, and why really everyone hopefully should get much more engaged in thinking really deeply about building materials and the role they have to play in combating climate change. So as you may know, currently buildings and infrastructure account for nearly 40% of total global CO2 emissions. And this means that we really have an essential role to play. So by many estimates, embodied carbon makes up nearly half of all of that impact together. For a very, very long time, the building industry has been really focused on building operations, on drawing down operational carbon, on strategies like energy efficiency, fuel switching. And this work is really, really important. It's work that we must do. It's work that we must focus on, but it's also not the whole picture. And what we've learned over the years is that if we just focus on operational carbon or building operations themselves, there's really no way for us to meet our global CO2 reduction targets. And there's no way for us to really stave off some of the most catastrophic effects of climate change. So it's really, really important that if we're going to make progress on this topic, that we actually look quite deeply at embodied carbon itself. So I'll start off and just ground us in a simple definition of embodied carbon, because it's principally what we're going to be talking about. So if operational carbon are the emissions associated with heating a building, cooling a building, running a building during its operations, embodied carbon are really all of the other emissions associated with the manufacturing, transport, installation, replacement, and end of life of all of those construction products. So that actually ends up being a ton of embodied carbon and a ton of emissions that for a long time were really just couched under this category of industry. So this action is really about architects, engineers, manufacturers coming together and saying, those are also emissions that we need to draw down. It's also essential because just at this critical moment when we need to radically decarbonize and decrease our emissions globally, we also need to build a lot. So it's estimated that between now and 2050, we're going to double the building area in the world. And that's not really just about superfluous building. This is about really thinking about access to core infrastructure, to housing, to schools, to healthcare, to all of the vital services that architecture and construction really serve. And so at the same time, we are going to be building a great deal. And we also really need to figure out how to work with the building stock we have and how to build smarter and how to build better. This focus on carbon and carbon emissions and climate change reminds us that actually a building project causes environmental impacts far beyond its building site. So it's really pushing architects and engineers to think radically differently about what our role is, who we're ethically responsible to, and how we think about our projects. So thinking broadly across supply chains, understanding where our energy comes from, understanding where the steel and concrete and cement and timber as well are made that go into our projects is really, really important. And we also understand that carbon emissions are not the only environmental impacts. So we have an awful lot to grapple with in understanding the relationship between material manufacturing, pollution, land use transformation, et cetera. And all of this means that we come back to this fierce urgency, that we really don't have a lot of time to lose, right? And that we basically have 10 years to radically decarbonize our entire industry. And this means that we have an ethical responsibility to retool our industry, to change the way we think about construction, and really to focus in on the kind of techniques you're going to see that the Lake Flair team is using on every project that we do. So this is really a huge call to action. And I would encourage all of the students or young practitioners that are on this call to really think about how they can work more impacts of climate change in construction, but also participate in this research. So the climate crisis, as I said, is forcing the design community to think differently about their projects and this responsibility we have far beyond our building footprint and beyond our immediate clients to this larger problem that we really have helped create. But also this is a topic that is much bigger than just engineering, and decarbonizing an entire sector of the economy is a highly collaborative process. So we're not going to spend a lot of time on this webinar talking about it, but there's really excellent research going on at Penn these days, really digging into what the role is in the collaborative relationships needed to bring together researchers and academia, non-government organizations, policymakers, the entire design community, manufacturers and industry, all together to really think about how we can work on this roadmap to net zero. But at the end of the day, the only way we're going to make any progress is if we actually measure embodied carbon on our projects. So how do we do that? Very, very briefly, the way that we measure embodied carbon globally is really through a process called life cycle assessment. So life cycle assessment is the evaluation of all the inputs and outputs and all of those potential environmental impacts of a product, in this case, a building material or assembly across its full life cycle. So as architects and engineers start engaging in LCA, they're really thinking across this full life cycle perspective of their building, from manufacturing, construction, use, replacement, and end of life. Increasingly, there's a number of tools and platforms available for architects and engineers to calculate embodied carbon and other impacts during design and construction, and some of those are starting to be taught in schools of architecture and design as well in engineering, which is something that I think we really need to build up this capacity across the industry. And those tools and the carbon disclosure and data that underlies them are fundamental to establishing the goal of setting carbon goals early in the design process, which the Lake Flato team is going to talk about with their case study, and also about bringing those design decisions all the way into procurement and actual construction, and making sure that those carbon goals are actually realized. So in recent years, we've made a lot of progress establishing methods and protocols in carbon accounting. And what that does, so through environmental product operations and other disclosure documentation, what that does is really enable architects, engineers, builders, and the industry more broadly to totally rethink how materials are made and the nuances of complex supply chains, the labor implications of decarbonization, and pave the way for rapid innovation across all material categories. One of the most exciting categories, I think, that really is what we're going to focus on for the whole rest of this webinar is mass timber. And you'll be hearing from the other speakers about some of the unique attributes of mass timber, and also how it makes is really important in terms of thinking about decreasing the carbon footprint of buildings, but also how it has a lot of other sustainability attributes, that it's a material that is generally non-toxic, it's durable, it's beautiful, it contributes a lot to our health and well-being, as well as really being a new novel technique for construction and manufacturing. But it also raises a lot of questions, and timber is a really interesting material for researchers to wrap their brains around. So, you know, it raises questions about, because really it asks us to look across these full and very, very diverse supply chains, all the way from forestry and land management on one side, through more traditional manufacturing of wood products, turning that timber into glulam or CLT, or even traditional timber products, dimensional lumber, and into lots of questions for design, construction, and end of life of where that wood goes at the end of it all. So key to a lot of this math is really this concept of biogenic carbon and how we can understand and make use of the ability of trees to sequester carbon in their biomass as well as in forest systems, and how we might hold that carbon in those forest stocks in the built environment. And I think I'll kind of leave it there now for the introduction, but I think our next speakers will all be grappling with these ideas of what the promise of mass timber is, what some of the challenges are that are coming up in increasing the volume and production of this technology, but also how I would encourage you to think about how mass timber really connects all of these different landscapes of concerns and helps us think all the way from what sustainable forestry management looks like out in areas far, far from the building site, what the labor implications and positive economic benefits might be of increasing the use of mass timber in the economy, and what this really means for the built environment, how we build and how our buildings really act back and shape us. So with that, I'm going to turn over to Terry. Harry, are you able to take the...
I am here and ready. And you can see my screen now. We all good?
Yep.
Great. Thank you, Stephanie. So I am broadly going to start talking about what is mass timber and heavy timber. How long have we been building with, wood in general? What are the considerations about timber construction? Some of the benefits of speed of construction, cost and labor, and then I'm going to wrap it up with what are some of the real and some of the perceived challenges that we kind of face today. So the first thing I'm going to start with is just kind of the language around wood. So again, when we're talking about light frame construction, the things that you are familiar with in your home construction, we're really talking about boards and dimensional lumber and things like that. When we start talking about timber, whether it's heavy timber or mass timber, it has to have more mass associated with it. And that's due in part to how it performs with fire. And we'll get into that a little bit later. So the smaller dimensional lumber is, again, not what we're going to be talking about today. We're going to be talking about timber. How long we've been building with timber? It's been forever. And again, there's mass timber falls under this category of heavy timber, but there is a distinction between the two. So if we look at the image on the left, you can see that these columns and these beams in this building are made from those really big, massive elements that came from one tree. If we look at the mass timber on the other side, we are looking at something that is made up of smaller elements that are put together. But the fact is that we have been building with both heavy timber and, and some engineered products for hundreds of years. So why are we talking about mass timber today? Again, let's just talk about mass timber again. We're taking small pieces of wood and we're putting together. Typically, it is with adhesives and pressure, but not always. So what are some of the materials that we are talking about today? Again, for our columns and our beams, those can be made up of glue lams, or they could be LVLs or Paris strand or laminated strand lumber. And the difference between all of these different materials is how the wood is broken down and put back together. So with glue laminated timbers, we're just taking a piece of lumber, and then we're going to cut out the best pieces of it and put it back together like that. Laminated veneer lumber, LVL, is similar to plywood, where we're taking a thin veneer of the wood, but LVL is we're going to orient them all in the same direction so that we get that strength out of those strands. The Paris strand, we're going to break it down. Instead of being a veneer, we're going to start getting into flakes or strands of material that we're going to be putting back together and engineering how this lumber should be, how it should be performing. So again, columns and beams we can do with glue lams, LVLs, Paraland, all those other kind of things. For our horizontal materials, we can take that glue lam and lay it down and use it as a plank material. All of these other materials, LVLs, Paris strand materials, OSB boards, all of those are made in really large billets. So they're usually produced in 8-foot widths on a continuous press. And then after these big tall billets are manufactured, that's when they're cut into 8-foot lengths or 10 or 12-foot lengths, and then shaved into the different thicknesses that we're accustomed to seeing at our home improvement stores. Cross laminated timber is like really big plywood. I'm taking 2x material and I'm putting them together, but again, that's oriented every other layer orthogonal from the last one. Nail laminated timber is one of the first ones where we're not adding glues. I'm just going to take 2x, stand them on end, and mechanically fasten them together. This material was used really heavily in the late 1800s and the early 1900s as factory floors and warehouse facilities and things like that, where they needed a real sturdy floor for the heavy equipment that was on those. Dowel laminated timber is fairly new material. It's again taking the same principles as nail laminated timber. We're going to stick that 2x on its end. We're going to put it in a jig, drill a hole through it, and then take a hardwood dowel and throw that into these softwood lumber pieces. And we're going to have a friction fit for these kind of things. Again, from mass timber products, we also have mass plywood panels. These are, again, going to be produced on the same kind of scale as cross-laminated timber. They're going to be 8 to 12 feet wide, and they can be produced up to 40 plus feet in width as well. How are we going to apply these different systems? Again, we can use them in the post and beam system. This one here we're looking at has glue lams for that post and beam system, and then the nail laminated timber is on the floor decking. The other way that we can do it is Brock Commons actually utilized CLT, which is a two-way slab system, and only have posts and these slabs. So we have a two-way panel system going here. No beams at all throughout this whole process. We could use bearing wall systems or honeycomb. And we're also starting to see hybrid systems, potentially with light frame walls as our bearing wall system, and then we're coming in with the mass timber to be our floor ceiling assemblies and our roof assemblies. We're also starting to see hybrid systems with steel and mass timber as well. So there's a lot of uses for mass timber in these systems. And people are always asking me, is it really happening here in this region? And I love to pull up this map because people always think of everything happening in the Pacific Northwest, and you can see how it is literally nationwide. The difference between the two colors on the map here is the gray ones are the ones that are currently in design, and the green ones that are either in construction or completed. And as you can see here, we had over 900 projects as of June of this year. Why would I consider using mass timber? As Stephanie alluded to in the beginning, there's a lot of opportunities for embedding carbon and all those other kind of things. But we also have the challenge for designers to recognize its durability and its strength. A lot of time people think of wood as a less efficient material than concrete or steel, but we really have to recognize what its structural performance is. So when we look at a steel beam and a wood beam in a fire comparison, if you look at what happens in 10 minutes, the temperature is going to be over 1,000 degrees, and the steel is going to already have gone into its plastic range and lose more than 50% of its structural integrity, where it takes about 30 minutes at almost 1,400 degrees for wood to lose between 20 and 25% of its structural strength. And the reason why this is again, we're talking about timber, so we're talking about having that mass. So similar to the way a tree protects itself in a forest fire, it starts to char on this outer edge, creating an insulated section that will protect the middle of the structural material, just like a tree does to protect its growth so it can survive a massive fire. Speed of construction is really important. So if you look at something like Brock Commons, we have 17 stories of wood started on June 6th, and 9.5 weeks later on August 10th, this building had all of its structure in place, the building envelope was in place, and all of the topping slabs were placed as well. What I also want you to recognize, if you look at these images here during construction, specifically look at the image in the middle and the one on the far right, you can see that it takes very few people. So you have a small labor crew and very fast construction, and these are some of the things that are really driving the benefits of mass timber in today's economy. Are we always going to see these kind of results? No. We have never seen a mass timber project that added more time to the schedule. We've usually see them providing somewhere between 20 and 85% compaction of that overall construction schedule. Again, that's provides a lot of savings for the construction industry. I'm going to take a look at this specific case study here. Candlewood Suites is building a number of hotels on military bases. So Lend-Lease wanted to use mass timber, and we had to go through blast testing and other things like that to get this material approved. But what they were able to do was this particular one, the Redstone Arsenal, was the first one they did. They've done several since then. The Redstone Arsenal was actually 14% larger than the ones that Lend-Lease had built previously for the military. But you can also see that the construction time, they saved over 37%. They used 43% fewer people, and they had an overall construction savings of 20%. And I believe that the overall cost savings on the project was in excess of 20% as well. So why do we have all this talk about mass timber right now? It really kind of started as we were starting to hear about cross-laminated timber. Cross-laminated timber is the newest technology in this mass timber world. It is about 40 years old. It's been in the European markets for quite some time. But in 2015 was the first time we actually put it into the code. And all we did in 2015 was added the language in chapter 2, which was its definition. And in chapter 23, we outlined that in order for it to be cross-laminated timber for building construction use, it had to meet the PRG 320 standard. And that is a standard that outlines what kind of adhesives need to be used, and what the lam stock needs to be, what the testing needs to be to verify it, all those other kinds of things like that too. The next thing that happened is that the individual regions have to accept those codes. So the challenge is right now, especially in the Mid-Atlantic region, there's not many jurisdictions that have adopted even the 2015 code. The exciting news is that when we get into the 2021 code, we're actually going to be able to start building really tall buildings with wood. Currently, right now, all buildings in type 2, 3, 4, and 5 construction are going to be less than 85 feet. Doesn't matter if we're adding sprinklers, doesn't matter what kind of construction material, doesn't matter what occupancy, it taps out at 85 feet. So any high-rise building is a type 1 building, which means that it's right now, the language says that it has to be non-combustible materials. But the 2021 code is actually going to allow us to do type 4A construction up to 270 feet. Because it needs to be consistent with that non-combustible material, 100% of this mass timber structure will be covered with drywall or something to help protect it. 4B, we're going to be allowed to go up to 12 stories, 180 feet. In that application, we are going to be able to expose a portion of the building. And in type 4C, we are going to stay under that 85 feet and have everything exposed. Another question I get is, can we actually get cross-laminated timber here in the US? Again, remember in 2015, we were just introducing it into the code. So we had no manufacturers in the US at all. We had a couple in Canada. What you are looking at here is a list of the manufacturers that are PRG 320-2018 certified. So they're ready for the 2021 code. And all of these manufacturers have met those standards and are ready to produce for the North American market. And all but 2 of these are now North American manufacturers. Over half of these are actually producing in the United States. And with that, I am going to turn it over to Heather, who's going to talk about what Lake Flato is doing. Thank you.
Thank you. All right, can everybody see my screen?
We can.
Great, thank you. So my name is Heather Gale Holdridge. I'm the Director of Design Performance with Lake Flato Architects. We're a 120-person firm in Texas. Most of us are in San Antonio, but we have a small studio in Austin, Texas as well. But we're doing buildings all over the country, and including on UPenn's campus. So I was an engineering student as well. My major is in mechanical engineering, and I studied engineering because I loved my high school physics class and loved hands-on applications. And I wanted to take those talents and use them to fulfill a larger purpose. So mechanical engineering seemed like the best way to impact energy, which struck me as our greatest opportunity to have a positive impact on the environment. And then I was surprised to learn how much energy buildings consume. So through a long story with plenty of twists and turns, that's how I ended up at an architecture firm. So as Stephanie described, carbon has become our profession's universal metric for measuring our negative impact on the environment and climate change. And the pie chart on the screen shows that embodied energy of buildings is significant right now, even for an average performing building. But as we make greater progress towards more energy efficient and high performing buildings, that embodied carbon piece of the pie is going to become much, much more significant. And at some point, it's actually going to outweigh the amount of operational energy. So that is why we've come to focus on that, so that we can make sure that we're addressing both sources of carbon in our design projects. So if we zoom in on that embodied carbon quarter piece of the pie, this is how it breaks down. So every material that we choose in our buildings has a carbon impact. The building structure, the frame, the foundations, et cetera, make up the largest portions. So the decisions that we make here matter the most when it comes to embodied carbon. Stephanie talked about life cycle assessment. So the tools that we use to measure from the beginning of the building's life cycle, extracting and sourcing materials, all the way through operations into the demolition of the building, how we quantify the carbon impacts. So this slide is somewhat misleading, because I think a typical designer's workflow does not include life cycle assessment at all, but hopefully we're making some strides towards greater adoption of that. But for the designers that are using life cycle assessment, they are typically only evaluating it at the very end of design. So all of the design decisions have been made, and they're quantifying how much carbon is associated with that building design. Our preferred method, and this is a slide, really great slide by Kieran Timberlake, so it's talking specifically about tally, but you could use other carbon tools as well as part of this process. Our preferred method is this lower workflow, where we're using life cycle assessment throughout the design process. So using it to inform design decisions, using it to evaluate different choices that we're making, so that we're always considering carbon as we go through the process. It's a much more iterative process and helps us drive down carbon as much as possible. Sorry, I'm having some trouble advancing slides here. So through those LCA tools, LCA stands for Life Cycle Assessment, we've gained an understanding of the carbon impacts of the major structural materials that we use. So these are expressed as box plots because there's a large range for each of these materials. It depends on many, many variables, including the location that it comes from, the manufacturer's process, whether or not you're using recycled content. So, but even with these ranges, we can still see that concrete and steel are not our most environmentally responsible choices. And these tend to be the most popular structural systems that we see in buildings. So mass timber starts to show us some promise here. So our two biggest tools for reducing embodied carbon are to reduce steel as much as we can, and to reduce the amount of cement in any concrete that we use. Upon further study of concrete, the cement has a significantly negative carbon impact. So the good news is that we can still use concrete and substitute that cement with other materials so that we can have more environmentally friendly options there. So you probably noticed in my box plot slide that mass timber is a structural option with less negative carbon impact. We studied a hospitality project we were working on in a high wind area of the Gulf Coast to see what the life cycle difference would be if we designed it with mass timber as structure instead of our originally planned concrete and steel framed walls. As you can see, the difference is significantly improved whether or not you include the biogenic carbon. And mass timber is so much more than a tool for designers to mitigate climate change in our buildings. It's also beautiful, it's a natural material, and it contributes to biophilic design. Biophilia may not be a word that you're familiar with, but it's a scientific term that describes humans' innate biological need to connect with nature. Using the natural warmth of wood helps us connect humans with nature in building design. To illustrate this, which of these two spaces would you prefer to work in? The space on the left uses natural materials, daylight, fresh air to connect humans to nature. And we love that you can use mass timber structure exposed because of its beauty. You don't have to add drywall and other finishes to cover it up. Those extra materials cost more money. They often include toxins and other undesirable, unhealthy ingredients. And of course, they have a carbon impact. So that we can use the structure as the final finish has a real environmental benefit as well. And the beauty and biophilic benefits of mass timber aren't just about enjoyment. There's real data and research demonstrating the financial benefits of biophilic design. These buildings are in higher demand because employees and students are performing better and getting sick less in them. So you can command higher lease rates whenever you use these materials. They also offer cost-saving benefits during construction. This is a photo of a mass timber project that we are working on at the University of Denver. This was in an infill site on an existing university campus, so our construction site space was pretty tight. Mass timber allowed us to work comfortably in that space and had less construction noise, which was very much appreciated to our nearby neighbors on campus. And showing just a little bit more data from that same University of Denver project, we were also able to save costs through a compressed construction schedule, and the panels that arrive on site are easy to assemble, so they require less time and less people for the construction as well. So clearly, our firm, Lake Flato, has become big fans and advocates for mass timber, and I think that is in big part because it connects to the core principles of our firm. As I said, we're a 120-person firm based out of San Antonio. We work on a lot of different projects now, including a building on your campus that Carrie will be speaking to. But we really started with projects like these. Texas Hill Country Ranch Homes. This is a net zero project where we carefully studied the site and the local climate to use passive design like natural ventilation and local materials to create a building that responds to its environment and is authentically linked to its place. So these are the driving design principles of our firm. We value design that is authentic, artful, and crafted, deep understanding of place and placemaking, creating and supporting community, and creating high performance buildings, high performance sustainable buildings. So mass timber fits with all of these and has been embraced as a way to further these design aspirations. So the last note before I pass this off to Carrie, I think our next steps in studying carbon and mass timber is that we're currently working to educate ourselves more on carbon and wood and to learn more about the wood supply chain. Forestry practices are critically important here. Wood is a renewable resource, but only if it's responsibly forested and not clear-cut. So our profession still has a lot to learn about wood sourcing and sustainable forestry. There are certifications for sustainable forestry that we are seeking to learn more about, including FSC. And we are understanding what we can request from manufacturers so that we can make sure that we're making the best choices here.
Great, thanks, Heather.
Here.
So now we're going to take all of that and apply it to a project, for the University of Pennsylvania. So you've been introduced to us, Lake Flato. Architecture and building is always a team sport, especially when we're trying to make a dent in carbon. So we're partnered with KSS. Together we make the architecture team. We have Burrow Happold. There are mechanical, electrical, and plumbing engineers, but there also are structural engineers and daylighting and wellness engineers. So there are wizards that are making everything happen and realizable. As we're thinking about this too, making sure that our dreams kind of are buildable and fit within a project budget is really important. So we're working with Gilbane as our contractor for pre-construction services, kind of testing all of these options and assigning kind of value to them. A little context for the project. Our site is on the corner of 34th and Chestnut and will become part of this engineering campus that you see in the kind of purple pink. The building will include instructional labs, classrooms, research centers, but the unifying theme for all of these program spaces is going to be data science. our very first meeting with Dean Kumar to talk about this project, he gave us some really aspirational goals. He started with framing the project to say we're designing something for a yet to be imagined future. No big deal, right? But he also gave us more tangible goals to design a building that was welcoming and enticing, that we balance all of the technology in the building with nature and biophilia. So we're creating a really humane, healthy environment for people. And that in that context, we're also stewards of environmental resources. So that's the lens that we've been measuring ourselves against as we design this building. The university also has its own climate targets, targeting reducing carbon emissions by 40% by 2024, which is surprisingly close. As we're working towards reducing the embodied carbon of the building, we start by really analyzing the structure. So we've started with 3 different structural systems. The first is our timber structure, where we've got 6 stories of timber. That would be glulam beams, columns, CLT slabs, and then we have a concrete basement. The next is a steel structure with steel beams and columns, a metal deck with a concrete topping slab, and again, a concrete basement. And the third would be an all concrete building, so 6 stories plus a basement of concrete. Burrow Happold ran that through their BOM model to analyze the carbon impact of each structural system. When we look at that, we see that the timber structure has a global warming potential of 120 kilograms of CO2 per meter squared. That's a 41% reduction over the steel structure at 204. And concrete on the far right at 252 is performing 24% worse than the steel. So that's a big, each structural system has a big improvement as we move towards timber. If we look at the pie charts, at the bottom, you'll see the gray area, which is the biggest chunk of each of those. Even in our timber building, the biggest contributor to carbon, to embodied carbon, is that concrete, which in this case is only the basement and the foundation. So innovating and making concrete better will have a big impact on buildings and their embodied carbon. So from there, we started to focus the structural systems that we're studying. So concrete doesn't really make sense for our project for a lot of different reasons. So we're looking at timber and steel. And this time we're going to run it through the tally analysis that Heather mentioned earlier, which takes into account a full life cycle assessment. The BOM model takes into account the kind of the product, so the timber, the steel, and concrete, to the building, while this tally analysis is going to take into account the full life cycle. So we get to look at end of life, the impact of demolition and reuse, but also the potential for timber to sequester carbon. And the result is an even greater savings in that timber structure. So from our steel building to our timber structure, we're seeing a 58% reduction in global warming potential. And that increased difference is really driven by the ability to sequester carbon. So if we look at the right, where again, we're looking at embodied carbon by material, concrete is still the biggest driver, but that timber actually becomes a negative number because it's storing carbon. What do all those savings mean in a way that's kind of comprehensible? 203 passenger vehicles driven for 1 year would generate that same amount of carbon. So we've saved enough to equate to more than 20,000 tree seedlings grown for 10 years. It's important that we not stop at the structure as we analyze our building's embodied carbon. So one of our next steps is to start to look at the whole building, the impact that the interior finishes and the envelope will have in addition to the structure. And as we look at that life cycle analysis, we're looking beyond just the carbon and the global warming potential, but also starting to evaluate it in terms of acidification potential, eutrophication potential, just like runoff, and smog formation, among others. So if we zoom in and we look at what those structural systems mean for the interior finishes and how that might affect our carbon, this is what our building might look like as a steel building right? So we've got our steel structure that's fire rated because of its size, which is kind of messy and ugly. So we've got it concealed by ceilings. Those ceilings are lower, and because of the quantity of ceilings, they're probably acoustic lay-in, which isn't the kind of ceiling that any of us as architects aspire to design, right? It's not the best environment. We still have the project goals of creating a space that's biophilic and warm and welcoming. So we're really relying on finishes applied to the walls and applied to the ceiling to create that atmosphere, which is added material and added cost. And the mechanical system gets concealed because we've got that cavity space between the floor and the ceiling to run things. If we look at the next option, this is our timber building. And because we get to express the timber, right? And all of its character for the ceilings and the columns and the beams. So we're applying a lot less material, and the material we're applying gets to be a lot simpler. The timber can be sized to address the fire rating requirements, so we don't have to add in that spray insulation. Again, a savings and a reduction in material that we're adding. We do have to consider acoustics a little bit differently in a space like this, so we're relying more on the walls to accomplish that acoustic performance. And in this building, we get to express the mechanical system, which seems really appropriate that in a school for engineering, you would be able to look in the building and see the engineering of that building. You know, this is important from a carbon perspective, but it's also been really important for us to study this with the contractor to understand the real costs of timber versus steel in the context of not just the structure, but all of the other parts of the building. And like everyone said, the benefits of mass timber are bigger than just carbon and bigger than just aesthetic as we think about our urban campus. We've got housing across the street. We've got a limited laydown area, and we've got really busy streets around it. So that faster construction that fits within university schedules, that reduced construction traffic, that's less disruptive to the city's flow, and it's quieter, which is good news if you're one of the students living in the college housing across the street. So it allows the university to be better neighbors during construction. And like everyone said previously, it contributes to biophilia, which has a really big impact for the university as we're looking at what it contributes to folks occupying the offices and the educational spaces with increased productivity, improved memory, increased rates of learning. The building helps make people better, not something they have to fight against. And of course, we're still having to consider operational carbon. So this is a study that Burrow Happold put together for us that compares a VAV mechanical system versus an active chilled beam. And we're starting to look at systems, not just its energy consumption, which is how we would have looked at it in the past, but also the carbon consumption of that system. And so we're seeing a 13% improvement in the mechanical system as it relates to carbon. And that is, right, that's every year that we're seeing that savings. So that equals the emissions to drive halfway to the moon every year, or to the carbon sequestered by 60 acres of US forest in 1 year. And I think Heather's gonna help me close that out, and we hope there's some time for questions still. I'd have to say that as we've put this presentation together, I've learned something in every meeting preparing for it. So there's just so much potential to continue to grow and evolve this conversation and to really make our buildings better.
Yeah, well said, Carrie. And I don't have much to add. And I know Stephanie will be closing us out so we can move to questions. We're looking forward to having a dialogue with you. But I just wanted to acknowledge that this was a lot of information. It sounded probably like more information than you could. The reality is that we are still at the very beginning of this process, I think, of truly understanding carbon and what we as designers can do to have a positive impact on the environment when it comes to embodied and operational carbon. So I would just encourage all of you to get involved in this if you're interested and passionate, because we definitely need more people to weigh in on this research and this analysis. We have much work to do. And I'd say the learning curve is still very steep. So this is a great time, I think, to be an engineer or a designer and to get involved in this body of practice. So thank you.
Wonderful. Thank you everyone for such amazing and really content-filled presentations. I think it was a real masterclass there in mass timber, of course, but I think also this real elegance of how, you know, designers are moving back and forth between the technical aspects of a material and also like how to really pull that together into a building and think about all of these different trade-offs. I think that was really amazing insight into all of those different elements of the design process. So we have only about 10 minutes left for Q&A, and I just want to really open that up. There aren't any questions in the Q&A tab. So if you're anyone in the audience, if you have a question, please go ahead and throw them in that Q&A tab, or if you prefer to put them in the chat, whatever's easiest. We have those both open. But just to get things moving till we have some more questions posted, you know, I just really could go out to anyone. I think that, you know, all of us have kind of at different times expressed this sense of humility that we have really a lot to learn, but also this united commitment to really rethinking construction and thinking about how we can make a difference on our projects. You know, since we do have a lot of folks from the university on this call, I'm wondering if any of you have some thoughts about what kind of research do you feel like would really support your work, and how could people support some of the questions that you have that seem pressing, either on the building and construction side, or you know, also for you, Terry, on trying to explain and help people understand mass timber more.
I can just offer that I feel like one area that it seems that it has not been studied deeply is mechanical, electrical, and plumbing systems. I think that, you know, we're starting with structure for logical reasons because we know that it makes up such a big part of the carbon equation in our buildings. But I'm really looking forward to learning much, much more about MEP systems. I think that the manufacturers have, I mean, there's so many different parts and pieces within it, so they're very complicated systems for us to break down and really understand the impact of each component. But until we understand that, I think that we're still kind of flying blind when it comes to making informed decisions about our mechanical systems. We can really only consider energy performance, but not the actual embodied carbon of the systems themselves. So that feels like an area that is just so ripe for opportunity.
We got a couple of questions now.
Yeah, let's see. So some lots of questions about wood, of course. So they're flying in. There's, you know, one here that I think we could take in a couple different directions, but someone just posted a question asking about what are the names or organizations and groups studying sustainability of wood grown and sourced to produce mass timber. So I can offer up just a few of the organizations. There's a lot of research happening on this topic, and I'd say the research falls kind of in two camps. I think it's a really interesting moment where we have a lot of mutual education to do. And I guess, as I had mentioned in the beginning, wood is a really long and complex supply chain. So there's a lot of conversations going on between folks on the forest ecology side, land managers, sharing their knowledge and research about forest carbon and some of the underlying mechanisms of forest carbon and how it works. And a lot of advances happening right now in our ability to measure and monitor. And then on the wood product side, there's just an incredible amount of learning that us ecologists have to do about how the forest industry works, forest markets, how sawmills work, how these complex supply chains, and also a lot of the social and labor implications of land ownership and management. So it's a really, really exciting time. I'll post a few names in the chat because most of them are acronyms. But one to mention that students, researchers might be interested is Quorum. That's the consortium of research on renewable materials for the US government. They do life cycle assessment and carbon accounting of wood products. A lot of work coming out of University of Washington, out of Oregon in the Pacific Northwest. There are a lot of data analysis groups that are using satellites and remote sensing to do forest inventories, and a lot of researchers that are out in forest systems actually measuring carbon itself. and folks from industry participating in the incredible gains in efficiency that have happened on the manufacturing, milling, logging, supply chain side. So I'll post a few names, but I don't know, Terry, if you want to take that question or add to it at all.
I was just going to say, just starting at the U.S. Department of Agriculture and their forestry, they are definitely working hard on every aspect of it, from the forestry side all the way through to, what can we do with the end of life. I was really, really fascinated. I found through the U.S. Department of Agriculture, there's a branch in Baltimore, okay, of all places, and they are actually working on deconstructing some of the brownstones that are been laid vacant there, and they're taking all that lumber and they've actually sourced with a furniture manufacturer, and they're creating a line of furniture from the timber. So it's going to be like Urban Design Baltimore, and they're also looking at doing the same thing. So there's a place in Detroit. So again, there is, through all of these different places, we're seeing the full life cycle and what we can do after its useful life in a building, and what we can do to continue to use these products. There's a number of places in the New England states as well. They're looking at both the economic impact on forestry, since a lot of their was going to paper and pulp mills, and that use is down dramatically. So they're looking at repurposing a lot of the forests there. The big thing that we have to recognize is that we need to sustainably use the forests more, so we don't have as many issues that we're seeing right now on the West Coast. We've got to figure out better ways to manage our forests. What's our next question there?
Excellent. So there's a question here about end of life. So Allison has a question asking how mass timber elements are dealt with at the end of the building's usable life. So where do they go? I don't know if
Good
Heather
question.
or Harry want to take that one.
Go for it, Heather. You got anything?
Oh, sorry, I thought Carrie was answering that. I think
Carrie, go for it.
I'll take it. So.
I would say that one of the things that we're starting to see from some engineers are deconstruction manuals for their buildings, right? That make it even easier to take those pieces and reuse them in other projects. But I think we can also look at how heavy timber is being used as buildings are coming down, right? That wood is still usable for other things. And I imagine that in this case it would be the same. I think, Heather, you probably know from the tally calculation, it's assuming that some of it's reused, some of it's ending up in a, demolished and not reused. But I think it feels like an area that we can keep doing better as we think of deconstructing our buildings.
Yeah, I was going to offer a similar answer. There's design for disassembly guidance, and we're certainly designing to that. And I think because of panelized nature of a lot of the mass timber products that we're working with, it lends itself very well to that. There's very clear guidance on how it was constructed and how it can easily be deconstructed and used for some other purpose when it's no longer the structure for the building.
And that was some of the value. Terry, you talked about nail laminated timber versus dowel laminated timber, even that shift to get the metal out of those panels so that the dowel laminated timber was easier to reuse. I think the industry's moving in that direction.
I think the challenge to answering the question right now is, again, we have a shorter history of wood structures. And again, I briefly kind of touch on the reason why is because when we first started our codes, it was in the early 20s, and they were developed by the insurance companies. So we're coming out of the Industrial Revolution. Iron and glass are the new big kids on the block. The insurance companies want to protect the asset, that building. We're not harvesting our trees and doing the heavy timber buildings predominantly because the structural grids were too tight for the big open spaces that we were trying to move into. So the only wood that was being used was our light frame materials. So the code started out with kind of a bias against wood. And as we know, all of these things kind of go from where we are to something new, which is nice to see this resurgence of mass timber and the direction in which we're taking wood now. So when we have done deconstruction of 1900 buildings and things like that, yes, those timbers are highly coveted for, you know, reuse and things like that too. If they're not used for structural materials, they are certainly put into finishes and furniture and things like that. There are some places that actually, more in Europe than here, use the part of the manufacturing stock as well as the end of life stuff to produce, you know, fuel and energy. So there's a lot of questions and answers to what's going to happen to it at the end of its life.
All right, I don't know, do we have time for one more question?
Oh yeah, throw one more at us.
What's a hard one? Does anyone, any of the panelists want to propose a question here? I mean, I think I wonder if we want to come back to this kind of like call for action. I think I hear from some of my architecture students all the time, an incredible interest in these topics. Sometimes a cynicism that designers or the construction industry doesn't care. And you know, Heather, Carrie, I'm wondering if you guys have any perspective on how, you know, if you see that changing. And you know, during my time in practice, I felt just the opposite. I feel like firms actually were really eager for and looking for students to come in and actually take up this charge, right? To lend expertise as our whole industry kind of retools and gains capacity. But you know, I'm curious what you're seeing, or if you have any words of advice for anyone who's graduating soon or really thinking about how whether or not their design, you know, education really aligns with their climate change goals and concerns.
I've been encouraged to see how design schools are continuing to expand the focus on environmental sustainability and building performance. So I definitely think that I'm seeing a lot of trends that are moving in the right direction. Still a lot more opportunity for improvement, in my opinion, but I think thankfully there are so many different organizations and resources that students can go and find that knowledge on their own. So I would just say that, you know, positions like mine used to be very rare within architecture firms, you know, having a dedicated role to sustainability and analysis and research. And I think that's becoming far more common. And I think what's even becoming more common than that is just an expectation that this doesn't have to be a specialty role within an architecture firm. All designers, engineers, architects, everyone who's touching buildings needs to make this a part of their regular practice. So I think that it's no longer become a specialty role or area of expertise. It's become expected that if you are a design professional, this is knowledge that you need to have and apply in your everyday work.
I think the only thing else, go ahead, Carrie.
Part of the question was also how our clients are approaching it, right? And what they're expecting. And I think, I can't imagine any of our clients that are going to go, no, we don't care. I think then it's our job to help validate that they can afford it. I think that's a lot of the cynicism that they approach it with, to go, oh, that sounds great, but we've got a budget. So being able to test options and work through those with our contractors, I think adds a lot to the success of implementing the things that we're all dreaming of.
I was going to piggyback on that as well. I was going to say, you know, if you're coming out of school with you know, a wish or a dream to make this really big impact on the world, the challenge is that when you get your first job and everything is more budget driven or anything else like that, you feel like your dreams are getting squashed all the time. What we have been able to try to reinforce through Woodworks is recognizing that these buildings are budget driven. Okay, we can't just talk about the sustainability and you know, some of the other the biophilic elements if it costs twice as much. So if you understand how the code can be used as a tool for you to give you better options, to include mass timber as or wood as an option, those are the kind of things too. So if you understand, you know, you broaden your education to where you understand how you can pull your dream into whatever you're trying to do with some of those more day-to-day functional budget-driven kind of things. I think that's would help us all.
All right, and I think with that we are out of time. So I hope all of this interest folks can channel into further conversation and further action on this topic. And we just thank you for all of your time and attention, and look forward to tuning into other great programming during Carbon Week. Thank you, everyone, so much.
Thank you.
Thank you, Stephanie. Thank you, Kerry, Heather, Terry. It's been a fantastic topic to discuss, and thank you for the advice you give to our students toward the end. And of course, for me, I learned a brand new word today, which I'm very proud of. I'm going to use in some circles to make myself look important, which is biophilia. That's a new word that I learned today, and it's quite fascinating, the work that you guys do. And we thank you again from all of us here at Penn Engineering for participating in this panel. Please join us tomorrow where we'll wrap up our climate week at Penn Engineering. Our topic tomorrow is a case for removing carbon from the air. And our special guest will be Professor Jennifer Wilcox, who will talk about this and her research and the work that she's been doing right here in Philadelphia. So from all of us at Penn Engineering, we thank you for participating. Hopefully we'll see you tomorrow. Thank you again, and goodbye.